All right, we're going to take a look at the extreme value theorem, and before we get into that, we're going to take a look at a graph and answer some questions. If you're in my class, this is in your packet and it's on page 1, so you can I would encourage you to stop the video at this point and do this warm-up by yourself, and then come back and look at the video and make sure that you answered the questions correctly, just kind of to check yourself to make sure you understand what you're doing. Alright, so before we get into the extreme value theorem, let's take a look at this warm-up. You've been given a graph, and the name of the graph is f, and there are particular values of x that have been indicated. There's a value at a, b, c, d, and e. So question number 1 in the warm-up says, using the graph above, determine the derivative. It really should say estimate the derivative, because you can't determine it exactly since you don't know the function or know the function values. But let's say estimate the derivative at b, c, and d. Alright, so we're considering the derivative at b. And if we look at b, it appears that there is a horizontal tangent there. So I would estimate the derivative to be 0. It appears to be a turning point at b. Looking at c, the same thing is happening. It appears that there is a turning point occurring at c. So the derivative, there's a horizontal tangent, so the derivative again would be 0. And looking at d, again, we have a turning point, and it appears that the derivative is 0. So I would say that the derivative at b, c, and d is 0. It says to justify your answer, I would say because the tangent line or tangent lines are horizontal, and as we know, horizontal line has a slope of 0. Number 2, determine whether the first derivative is positive or negative on the following intervals. So the first interval we're looking at is the interval from a to b, and I'm going to change colors to red for that. So we are considering the first derivative from a to b, so I'm going to color that portion of the graph. Now if we think about the tangent lines in that portion of the graph, and we were to trace the curve or follow the curve with tangent lines at those points, I think we can see that the first derivative on that interval from a to b is positive. So the first derivative is positive. Maybe let's make a little chart here. Let me get rid of that. So let's consider two things. On this interval, we said first derivative, and the other thing I'm interested in that we'll talk about and kind of confirm later is what's happening with the original function. We said the first derivative is positive, and the original function, notice on that interval, is increasing. Okay, let's take a look from b to c. So from b to c, the first derivative, again, if you think about your tangent lines, the tangent line for that entire interval would have negative slopes. So we would say on this interval, the first derivative is negative, and the function itself is decreasing. Okay, let's take a look from c to d. So if we travel from c to d, we're talking this interval right here. Again, we can see the slopes change back to positive, the slopes of the tangent line. So on that interval, the first derivative is positive, and the original function is increasing. By now you probably have started to make a conjecture, but again, we'll confirm that conjecture a little bit later. The last interval is from d to e. So if we travel from d to e, this interval right here, the slopes of the tangent lines in that interval would be negative, and the function itself is decreasing. So first derivative on this interval is negative, and the function itself is decreasing. Question number 3. Determine whether the function is decreasing or increasing on these intervals. Justify. Well, to justify, we would say the graph is either going up or going down, and the good news is this. We already answered these questions. So on a to b, the function was increasing. On b to c, the function is decreasing. On c to d, the function is increasing. And from d to e, the function is decreasing. So that's pretty good. We got that knocked out of the way. Let's take a look at the next statement. Oh, that's it. All right, so we got that out of the way. Pretty easy stuff there. All right, now let's get into the extreme value theorem, which is the focus of this video. The extreme value theorem, and the plural of extreme is extrema, so that indicates there could be more than one extreme value, and the extreme value is referring to the maximums and the minimums. I actually want to add that word in there because that's an important word. The maximum would be the highest y value of the function. The very highest y value of the function. Now it's possible that the graph could hit that y value multiple times, but there is only one highest y value that we'll be able to identify on a graph, and the absolute minimum. Oops, actually, let's back up here. I'm not talking the extreme values yet. All right, so let's back up. Extreme values, maximums and minimums. And then there are two types of extrema. Sorry about that. The two types of extrema are, number one, absolute, and this is what I was talking about just a second ago. There are absolute extrema, or global. This is another term to refer to that. Those are the lowest or highest y value over the entire domain of the function on a closed interval. That's very important, and we're going to look at that in the notes a little bit later. So the absolute is the absolute highest, the absolute lowest, or the global over the whole thing, the global highest or the global lowest. So let's identify the absolute maximum and minimum on the graph above. And notice that we do have a closed interval because this function is only defined, or at least on this graph, from A to E. That is our closed interval, so we have met at least the criteria in this definition of the absolute extrema. The highest y value that we see occurs at D, and the y value itself is f of D. So the absolute max occurs, and this is important that you distinguish the difference between where it occurs and what it is. It occurs at D, but the absolute maximum, because the maximum is a y value, and is f of D. We don't know the actual numeric value, but we know that if we wanted to compute the numeric value, we would substitute the x value into the function. So the highest y value occurs at x equal to D, that's your input, and the actual maximum is f of D, that's your output. Then we want to find the absolute minimum, or the lowest y value on the graph, and that occurs at A. So we would say the absolute absolute min occurs at x equal to A and is f of A. So the x value that generates this is A, and the y value itself, which is the absolute minimum, is f of A. Pretty easy stuff. You could have done this in Algebra 1. We'll get to the calculus in a second. All right, so the other type of extrema that we can consider are relative or local extrema. So instead of looking at the entire graph and finding the highest y value of all or the lowest y value, now we're looking kind of like in little neighborhoods, relative, local. So we're looking for any high, a hill, or any low, a valley. So basically we're talking here turning points, and that's what you see right here. So if we wanted to identify local extrema on the graph above, well, if you look for the turning points, we kind of did this in the warm-up. There's a turning point at B, so this would be a local maximum because it's higher than any other y value in that little neighborhood. It's not the highest y value of the entire graph, but in that little neighborhood of values, it's the highest y value, and it's also a turning point. And you also notice from the other side that the derivative there was 0. We have a local minimum occurring at C. because it's the lowest y value in that little neighborhood, not the lowest y value of the graph. Also, it's a turning point, and also notice that the derivative there is 0. Now, at D, remember we already said that there was an absolute max occurring at D. But the absolute maximum can also be a local maximum, because in that little neighborhood, that is the highest y value, and it is a turning point, and note that the derivative there is 0. So, a local max can be an absolute maximum, but it doesn't have to be, as you can see from what we did at B. So those are our relative or local max, local mins, basically looking for turning points. Again, you did a lot of this in Algebra 2. All right, another definition that you're going to need here is a critical number. The definition of a critical number is an element or elements of the domain. In other words, they are x values of a function where the derivative is either 0 or is not defined. So if we want to find a critical number, we set the first derivative equal to 0, or we have to figure out where the first derivative is undefined. Any value of x that makes the derivative 0 or undefined is a critical number. And what I want you to remember about critical numbers is this. Critical numbers have potential. So in and of themselves, they're not hugely important. We're going to determine if a critical number becomes something else. So for now, just remember, critical numbers have potential. Identify any critical numbers on the graph above. Well, we can see from the graph above that the derivative is 0 at B, the derivative is 0 at C, and the derivative is 0 at D. So we have a critical number. So B is a critical number, C is a critical number, and D is a critical number. Why? Because f prime of x, the first derivative, is 0 at these values. Now you're probably already noticing, kind of interesting. At each critical number, there's either a local maximum or a local min. That's not guaranteed, but as you can see from the notes, we've identified the critical numbers. What do you notice that occurs at the critical numbers? Well, at these critical numbers, at each critical number, there is, at least on this graph, a local max or a local minimum. Now look at the next statement. This is the important part. So so far, if this is where we stop, you might determine or decide that, oh, if I find a critical number, then I'm either going to get a local maximum or a local min. And that does happen very often, but look at the next statement. Give a counterexample. That means prove this isn't true for the following statement. A local maximum or minimum, here's a very dangerous word, always occurs at a critical number. Okay, stop the video, think about that, and sketch a graph or come up with a function that you think would prove that a value can be a critical number, but a local max or a local min doesn't have to occur there. Again, I encourage you to stop, think about it, try to figure it out for yourself. All right, so think about the graph of y equal to x cubed. Here's an easy example of a function. The derivative of first derivative of x cubed is 3x squared, and if we want to find a critical number, according to the definition, we take the first derivative and we set it equal to 0. So we divide by 3 and take the square root of both sides, and we get x equal to 0. So at x equal to 0, we have a critical number. Now the question is, does a local max or a minimum occur at x equal to 0? That's really the question. Well, look at the graph. The graph of x cubed looks something like that. Oops, let's kind of make that a little fatter there so it hits the... Oh, you know what? Let's start again. I think my pen is off calibration a little bit. All right. So we're going to sketch a graph of y equal to x cubed. So it looks something like that. And notice that at 0, we don't have a turning point. And so therefore there's no local max, there's no local min, which proves that if a value is a critical number, it does not necessarily guarantee a local max or a local minimum. So we have to test that out, and that's coming up later in another discussion. But what I want you to remember, critical numbers, they have potential. What do they have potential for? They have potential to be or become values where there is a local max or a local minimum. But just because you're a critical number does not guarantee a local max or local min. All right, now let's get back to extreme values. Remember, the absolute extreme value, what we're looking for is the highest, lowest y values. And if you look back at our graph over here, the highest y value occurred at a critical number. The lowest y value occurred at an endpoint. And that's important for identifying local extrema of a function. And before we write down the steps of finding the local extrema, let's look at the extreme value theorem. The question is, does every function have an absolute maximum and a minimum on a closed interval? Well, the extreme value theorem guarantees that under the following conditions, and the conditions are very important. If f is continuous, condition number 1, on a closed interval, condition number 2, if those two conditions occur, then there is a guarantee. So these are the conditions up front, conditions. You got to know the conditions. And then back here, at the then part of the conditional statement, that's the promise or the guarantee. If the conditions occur, then the function has guaranteed both a minimum, and notice it says a, that means absolute, a minimum and a maximum on the interval. All right, so the conditions of this theorem, before we can apply it, is we have to have a continuous closed interval. So there can be no breaks, gaps, or holes on the closed interval. The function itself might have discontinuities, but on the closed interval there can be no discontinuities. The conclusion or the promise or the guarantee of the function is there is a local max. Sorry, not local. There is an absolute max and an absolute minimum. Now the function may hit that high y and that low y multiple times, but there's only one high y, and that's what we mean by absolute max, high y value, and an absolute min, the low y value of the graph. Now the reason that the function has to be closed, if you think about it, if we didn't close the interval and we had a graph that goes on forever, let's say it's something like that, well, there's no absolute maximum and no absolute minimum on this function because it goes up to infinity and goes down to negative infinity. So we have to have a closed interval. So once you meet the conditions, that's the first thing to check for. Does the function meet the conditions? Then to find that absolute minimum, because the absolute extrema will occur at either the endpoints or critical numbers. So the first thing we have to do is identify the endpoints. Well, they're given because that's going to be your closed interval. Secondly, we have to find the first derivative, and we set the first derivative equal to 0 to locate the critical numbers, because the absolute extrema will occur let's spell that better. The absolute extrema will occur at endpoints or critical numbers. So we identify the endpoints. We set the first derivative equal to 0 to locate critical numbers. We're going to make a table. This is, you don't have to make a table, but it's just a good way to organize your information. And substitute endpoints and critical numbers. This is important because kids get mixed up here. Into the original function. Because remember, we're trying to figure out the highest y value and the lowest y value. Compare y values and decide. Make your decision. Those are the steps to finding the absolute minimum and the absolute maximum of a function on a closed continuous interval. Let's look at a couple examples of that. Locate the absolute extrema of the function on the given closed interval. So think about the function x to the fifth. It's a power function. A power function is continuous. So we have that criteria checked off. They've given us a closed interval. We have that criteria checked off. So remember, if the conditions are met, then there's a promise that there will be a highest y value and a lowest y value. So step number 1 is to identify the endpoints. So we have that. That's given. The next thing we need to do is to find the first derivative of the function. So I get 5x to the fourth minus 20x cubed plus 15x squared. Let me check that. 5x to the fourth minus 20x cubed plus 15x squared. That is correct. We're going to set that equal to 0 and solve. So on the right-hand side, I'm going to factor out a 5x squared, which leaves me with x squared minus 4x plus 3. Factoring again, I get 5x squared, x, and 3, and 1, and minus. So x is equal to 0, x is equal to 3, x is equal to 1. Those are my critical numbers. So I have identified all of the candidates for absolute max and min, so I'm going to create a table. So here's x, here's f of x. Over here are the candidates for winning the prize of absolute max and absolute min. I'm going to put them in numerical order. So the lowest x value is -3. Then we hit 1 and 0 and 3. Now notice one of the critical numbers happens to be an endpoint. That's perfectly fine. However, if you get a critical number that's outside of the closed interval, you don't consider it because you're only considering what's happening on the closed interval. All right, so then you're going to grab your calculator, which I already have up here. Notice I've already typed the function into my calculator. I have two functions in there. The second one is turned off. There are a number of ways that you can generate the values that you're looking for. I'm going to show you one way to do that in case you've never seen this before. If you go to second table set, notice that my calculator is set on auto for the independent variable. You can actually go to that, let me arrow down here, and change it to ask. Maybe you've seen this before, maybe you haven't. Select enter and then go second table. And notice that there are no table values there because the calculator is waiting for you to ask for the x values that you want. So I'm going to put in -3, and I get -763. I'm going to put in 1. Multiple ways that you could do this. 21, 0 is 20, 3, -7. All right, so we want to identify the high y and the low y. The lowest y value, so the absolute minimum, is -763. The y value is the minimum. It occurs at -3. And the highest y value occurs at x equal to 1, and it is 21. So we have our absolute maximum. Okay, easy stuff. Let's do one more because the other function has something interesting that I want you to see. Problem number 2. We have to check whether or not 2x minus 3x to the 2/3 power is continuous or not. It is a power function and it is continuous, so that's okay. We have a closed interval, which is given, so that's okay. So the conditions are met, so we know for sure that this function is going to have an absolute maximum and an absolute minimum. So we have our endpoints. We need to find the critical numbers by taking the first derivative, so y prime is equal to 2 minus, using the power rule, 2/3 times 3 will give you 2x, decrease the power by 1, to the negative 1/3. Now we have to set that equal to 0, and when I do, I'm going to rewrite this as 2 minus 2 over the cube root of x. In other words, I'm getting this what I would call algebra ready so I can solve the equation. Now I could get a common denominator on the left-hand side, but I'm just going to subtract 2 to the left-hand side, which gives me negative 2 over the cube root of x. Actually, I don't really have to go much further, because think about this. The first derivative is set equal to 0. Notice that I have x in the denominator. And this is the part that students forget about when they're dealing with critical numbers. When we set the derivative equal to 0, we don't get anything, but if we're the first derivative, sorry, I'm stumbling over my words here. Remember, for definition of a critical number, where the first derivative is undefined is also a critical number. And this first derivative is undefined at x equal to 0 because division by 0 is undefined. So the point of this particular problem is to remember that it's not just where the first derivative, critical number is not just where the first derivative is equal to 0, it's where the first derivative is also undefined. All right, now let's finish solving the equation to see if there's anywhere where the critical number is equal to 0. We found where the critical number is undefined, or where the first derivative is undefined. So to solve this, I'm going to cross multiply. And when I cross multiply, I will get negative 2 cube root x is equal to negative 2. Divide both sides by negative 2, and I get cube root of x equal to 1. Cube both sides, and I get x equal to 1. All right, so I have a critical number at 0, a critical number at 1, and then I have my endpoints. So I'm going to make my table. So x, y, I'm going to put the candidates over here in order. So the first value is negative 1, 0, 1, and 3. I'm going to go to the original function to get the y values. So here's my calculator. My second function is in there. I've already turned the function on. Also notice that when I put the 2/3 power into the calculator, I have to put that in parentheses. I'm going to go to the table, which is already put on set on ask. I have negative 1, 0, and 3 in there. So the y value at negative 1 is negative 5. The y value at 0 is 0. The y value at, is this for the right function? Yeah. Yep. The y value at 1 is negative 1, and the y value at 3 is negative 0.2403. Now remember, we're looking for the highest y value. The highest or greatest y value occurs at 0. So this is the absolute maximum. The lowest y value is at negative 1. So that's the absolute minimum. And let's take a look at the graph. So another thing we could do just to verify what's going on here is we could say second calc value. So we can see at negative 1 There is the y value of negative 5. At 0, the y value is 0. At, where do we go? 0. At 1, the y value is negative 1. And at 3, the y value is negative 0.2403. So just a confirmation that we did this right. If you are in my class, a couple more resources that you have are on my Edline page. There are 2 more videos on the extreme value. They're not my videos, they're videos from someone else that I just linked to my page that just could support you if you need more work on the extreme value theorem.